In this video, I'm going to be writing answers in scientific notation. Now, you'll see from some of the example questions why you might want to do that is because when you work out an answer in physics, you may well end up with too many significant figures. If you write too many significant figures, you're going to lose a mark. So one way of getting around this is to write the numbers, say, to a suitable number of significant figures, and I'll be telling you what a suitable number is in scientific notation. And this is obviously for very small numbers and very large numbers. Easiest thing right now is just to show you an example question. So this one says, example 1, a physics teacher builds the following circuit to calculate the current in the 4.2 kilo ohm resistor. Now we've got resistance here, 4.2 kilo ohms. We also have supply voltage, 6.0 volts. Both of those numbers are written to two significant figures. So that really means that my final answer should also be written as two significant figures. Now, if you don't know the equation, don't worry, because I'm going to tell you that we'll be using Ohm's law. V is equal to IR, and I'll rearrange to work out the current, and that's I, the current I is equal to voltage V divided by resistance R. So that gives us, of course, 6.0 divided by 4.2 kilo ohms is 4.2 times 10 to the power of 3. Now, if I just plug that into my calculator, 6.0 divided by 4.2 times 10 to the power of 3, I get an answer of 1 over 700. Now, I don't want to write my final answer as a fraction. That's not allowable. So press the SD button. You can see there's a few dots above some of these numbers. That just says that there are recurring decimals in my answer. So I press SD again, and I get this number here. So, in fact, I'll write it on the next line. 0.00142857142, and of course it's in amps. If I was to write this as the final answer, that's what the calculator's telling me, I would actually find that I would only get 2 out of 3 marks. So as I said, the numbers here, 6.0 and 4.2, that's 4.2 kilo ohms, they're written to two significant figures. My final answer should also be written as two significant figures. Now, I'm allowed anything up to 2 too many and 1 too few. But if I've got all of these are 1, 2, 3, 4, 5, 6, 7, 8, 9 significant figures there. We don't count the leading zeros. So to give that as two significant figures in scientific notation, it's going to actually be the first non-zero number here is the 1. The next one is 4, and the next one after that's 2. If I want to write as two significant figures, I actually just have to look at the first 3 numbers. Now, the reason, at least the first 3 non-zero numbers, the reason that I'm looking at the third here, because if this number is 5 or above, then I then have to round up this number here. Now, it's not in this case, it's a 2. So I can just write this number here as 1.4. It's going to be 1.4 times 10 to the power of, now this is a very small number, much smaller than 1, so it's going to be 1.4 times 10 to the power of negative something. So it would be times 10 to the power of negative 1, negative 2, negative 3, or whatever. To find out, what we have to do is, well, I've written 1.4, and basically I have to look where the point is here and work out how many positions to the right I need to move that point to get it between the 1 and the 4. So that would be 1, 2, 3 positions to the right. So that means this number, well, in fact, this number here can also be written as 1.4 times 10 to the power of negative 3 amps. And of course, that's much, much neater than this. But as I said, if I write all those figures there, I'm actually going to lose a mark, and I'll only get 2 out of 3 for that question. So that's very small numbers. Let's look at the next example, which as far as I remember is a very large number. So example number 2 says, all electromagnetic waves have a speed of 3.0 times 10 to the power of 8 meters per second in air. Calculate the frequency of a wavelength 0.17 meters in air. So again, don't worry if you don't know the equation, because I'm going to tell you the equation is V, write it here, V is equal to F lambda. Now this V this time is actually speed and not voltage as it was before. It's also a lowercase v. And I'm going to rearrange that equation to give me frequency F is equal to V over lambda. And V is 3.0 times 10 to the power of 8. The wavelength, now what was that wavelength again? 0.17 And when we work that out in the calculator, in fact, I'll write this down in the next line. We have, let's find out, so 3 times 10 to the power of 8 divided by 0.17. That gives us a massive number. Now again, if I was to write all of that down, I'll write it here just so you can see, but you don't obviously write this down in the exam. There is always a danger that if you are writing it the full answer, as I'm doing here, you could copy that down wrongly. So what I would actually suggest to do is to skip this stage here and just go straight for the shortened version. And again, if we look at the numbers that we're given, we have got 3.0 times 10 to the power of 8, that's 2 significant figures, and a wavelength, you don't count this leading 0, so 0.17, that's 2 significant figures there again. This final answer should be written to 2 significant figures. So if I'm writing to 2 significant figures, as I said before, I need to look at the first 3 figures. I've obviously got no leading zeros there. So the first 3 figures are 1, 7 and 6. Just as before, if this number here is 5 or above, I then have to round up the second figure. So that's the case in this, well, that's the case in this case, it's a 6. So because that's 5 or greater, I have to round up the 1.7 to 1.8. So I would actually write 1.8. But what is it? It's 1.8 times 10 to the power of something. It's times 10 to the power of a positive number. What I should also say is this is frequency. So that should have been in hertz. But as I also said, I wouldn't write down this number just in case we copy it down wrongly. So I would go straight from this, the substitution, to the answer. Now at the moment, what I have is 17647058882. And if I was to continue that number, it would also be 0.00000. That would continue. The point would basically be here though. So what I now need to do is to move the point, before we're moving it to the left, here we have to move it, before we're moving it to the right, here we have to move it to the left. So that ends up between the first 2 figures. And that'll tell us basically our power here. So we need to move it to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9 positions to the left, which means that this answer is 1.8 times 10 to the power of 9 hertz. Again, why we're doing this is obviously it looks far, far neater, but if you write this full answer, we're going to lose a mark because your final answer should, as I'm going to say it again, should have the same number of figures as the number in the question with the least number of figures. So in that case, and also in the previous question, that's 2 figures. Now, for the next 10 examples, I'm basically just going to show a number. And what I would like you to do is, you can either write it down or you can just think what that would be in scientific notation. And in all cases, that would be, if you can do it to 2 significant figures as well. And I'll give you a few seconds for each one, and then I'll show you on screen. Here is the first one. So we have a resistance of 2812500 ohms. If you want to pause the video now and then play it when you're ready. Okay, so this first number, I'll just write it down, in fact, is 2812500 ohms. Again, the point would basically be here, right at the end. And I would actually have to write that like so. So look at the first 3 figures. The third one, in fact, is just a 1. That's less than 5. So in that case, I don't need to round up the second figure. I'm just going to write 2.8. And it's times 10 to the power of. So to get the point between the first 2 figures, I'd need to move it 1, 2, 3, 4, 5, 6 positions here. So that means that this number here can be written as 2.8 times 10 to the power of 6. And then, of course, I want to add the unit. Let's look at the second one. The second one is a current, and it's obviously very small, so it would be times 10 to the power of negative something. So I'll write down the number again, move this up slightly, and I have got 0.000638,298 amps. Now, if I look at the first 3 of the non-zero numbers, so I ignore these zeros here, The third of those is an 8, so of course that is bigger than 5. So remember, if this is 5 or larger, I then have to round up the second value. And that means that rather than writing 6.3, that's going to be 6.4 times 10 to the power of negative something. Now, to work out this power here, I have to work out how many positions I'm moving that dot to get it between the first and the second non-zero number. So that's going to be 1, 2, 3, 4 positions. So that's 6.4 times 10 to the power of negative 4 amps. Next one, and remember we have 3 of these. Move this up again. The next one's a charge, 0.00, write that first, 0.002112 coulombs. And again, find the first 3 of the non-zero figures. I've got a 2, a 1, and a 1. This is obviously less than 5, so I just need to write the first 2 with the point between them. So it's 2.1 times 10, and obviously it's a small number. So it's going to be times 10 to the power of negative something, and I need to get this point between the 2 and the 1 here. So I'm moving it 1, 2, 3. 3 positions. So 2.1 times 10 to the minus 3, and as I said, it's a charge in coulombs. Next one. Move this up slightly. Now this is a frequency in this case, and it's obviously a large number, 78650, and it's hertz. That would be equal to, so again, look at the first 3 figures. Now the third one is, if this was 5 or larger, I had to round up this number here. So I have to write that as 7.9. And it's times 10 to the power of, it's going to be a positive number here. So again, the point would be there. And to get it between the first 2 figures, I need to move it 1, 2, 3, 4 positions to the left, which means it's 7.9 times 10 to the power of 4. And frequency is in hertz. Number 5. So this is a distance, could be a wavelength, but it's measured in meters anyway. It's 0.009175 meters. Now, first 3 figures which are non-zero are 917, so this is obviously 5 or greater. So that means I need to round up the second figure. So this is going to be written as 9.2 times 10 to the power of, now it's a small number, it's obviously much less than 1, so it's times 10 to the negative something, and I need to move this point 1, 2, 3 to get it between these first 2 non-zero numbers. So as I said, 1, 2, 3, so that means it's 9.2 times 10 to the power of negative 3 meters. Number 6. So we now have an activity in becquerels, and it's 375,260 becquerels, which would be equal to this third figure. Again, if this is 5 or greater, then of course what we need to do is to round up the second figure. So that would give us 3.8 times 10 to the power of, let's find out now, the point would actually be there after the 0. So I need to move it between the 3 and the 7 here. Move it 1, 2, 3, 4, 5 positions to the left. So 3.8 times 10 to the power of 5 becquerels. Number 7. So this is a time. So let's see, 0.0000625, and it's in seconds. And that would be equal to, again, this third non-zero figure is 5 or greater. So that means I need to round this up to 3. So it's going to give us 6.3 times 10 to the power of, it's obviously a very small number, it's times 10 to the negative, because I'm having to move this point to the right, get it between the 6 and the 2 there. I need to move it 1, 2, 3, 4, 5 positions. So that's 6.3 times 10 to the power of 5. Sorry, negative 5 seconds. Next up is number 8. Right, that's a big number there. So 2268000 joules per kilogram. That can be written as, looking at the first three figures, the third one is a 6, so obviously it's 5 or greater, so I need to round this up to 3. So that would be 2.3 times 10 to the power of, obviously it's a very large number, so that would be a positive power. So 2.3 times 10 to the power of, well, the point would be here. I need to move it between the first and second figure on the left. So that'd be 1, 2, 3, 4, 5, 6 positions to the left. So 2.3 times 10 to the power of 6 joules per kilogram. Just 2 to go. So this is number 9. Another large number. So what is that? 57,503 watts. That's a power. A third figure here is a 5, meaning I need to round up this number here to an 8. So that gives me 5.8 times 10 to the power of, well, at the moment the point would be here. And I would need to move that 1, 2, 3, 4 positions to the left to get it between the first and second figure here in the left. So as I said, 4 positions to the left means that's 5.8 times 10 to the power of 4 watts. And here's the last one. So we'll move this up. The last one is 0. How many points are there? How many zeros? 1, 2, 3, 4, 5 after the point. 1, 2, 3, 4, 5, then 7955 meters. Now that can be written as, let's see, so I've got 79, then I've got a 5, so that obviously means that this number has to get rounded up. So it's already a 9. So in that case, I guess I have to look at these first two figures. Now think of that as 79, and of course if I'm rounding this up, because I've got 5 here, this would be rounded up as 80, or 80. So I'm going to write 8.0 times 10 to the power of, and again I just need to move this point from this position so that's between the first two non-zero figures over here, and that'll give me the power. So obviously a negative power, that's a very small number. So 8.0 times 10 to the negative, let's see, 1, 2, 3, 4, 5, 6 positions. So 8.0 times 10 to the power of negative 6 meters. And there we have it. Those are our 10 examples. Fingers crossed, that'll save you from losing a mark if you write too many figures. That's certainly one thing that you want to avoid in your final exam. For now though, that's us. We'll see you later.